Okay, so what I've got here is a circuit on the board. We're gonna look at this two ways. One is we're gonna look at it as a series parallel circuit, and then we're gonna look at it as a, actually no, we're gonna look at it as two ways. The first we're gonna look at it as just a parallel circuit, and then we're gonna throw the series concept into it. Okay, good. So here we go. This is why, what we're gonna focus on is why this formula, okay? So I'm gonna say, and we're gonna calculate the current going through here. So this is my R2, R3, and that's obviously my R1. Why? Okay, we're going to do this. So the current through R3 is equal to, as we know, IT divided by some ratio where my total resistance goes on the top, and then the resistance of the actual resistor that's dividing the current goes on the bottom. So I'm just going to write here RT, and then I'm going to write here R3. Now, what we're going to do is focus on why this RT isn't the total resistance of this whole circuit. Okay, so let's break this down. What I want to do is I'm going to put a switch in here, and I'm just going to have that switch. So I'm going to bypass that. I just completely bypass that resistor. So if I were to close that switch, let's just say the current was 100. So if I close that switch and then I just wrote 100 on here, I have a parallel circuit where I have two resistors and I've got 100 amps going, 100 milliamps going and being divided amongst them. Okay, so then what I would need to do was I would use the current divider, which is this formula, and my RT would be the total resistance of these two. Let's actually just calculate that now. So I'm going to write down here R2 in parallel with R3. That total resistance is going to be 600 to the negative 1 plus 400 to the negative 1, which ohms, which equals 240 ohms. Okay, good. So the total network here is 240 ohms. And I know that if I needed to do this formula here, that's fine. That's going to be 100 milliamps. And in this case, it's going to be 240 ohms divided by 600 ohms. And that's 40 milliamps. Okay. Okay, so, and I know you're fine with that. You'd be like, okay, that's fine. Although you may have a little bit of problem with the fact that that's 100 milliamps, but let's just say I said it. Like maybe just pretend I just erased this whole thing and I just put a line through there and then I just labeled it as 100 milliamps. Okay. Whatever the voltage is here, we could calculate what that would be, but we're not going to do that. Okay, so we've solved that and we've seen that these two divide the current that's going into this node. The current that's going into that node, so this current that goes into the node, the current right there is divided amongst those two resistors. And we use this formula that tells us how those two resistors divide up the current. So when I'm looking at what the total resistance is, I'm looking at the total resistance of the resistors that are dividing the current. Okay, so now we're going to open the switch. I'm going to open this switch up and I'm going to say, we're obviously going to have to change the voltage a little bit if we still want 100 milliamps. Let's just say we did that. Okay, so now again, I've opened the switch. Now that resistor is in the circuit. The current is still 100 milliamps because we changed the voltage a little bit. Now we got the current's going in here. The current's going into this node. So that node has 100 milliamps going into it. Absolutely. So with that said and done, I want to know how these two resistors, I'm just going to say it all over again, but really, I need to do this. These two resistors are dividing up that current, or more specifically, this current. Even though that current is going through R1 right now, because my switch is open, that current goes through R1 and it's divided amongst these two. Now, don't try and think about why that's 100. It's 100 because this voltage is whatever it is. Again, we're not going to calculate whatever voltage is needed here to make 100 milliamps go through there. Just do it if you want. But 100 milliamps is going through here, it's getting to there, and it's being divided amongst these. Our current divider formula looks like this, and that RT is the total resistance of the resistors dividing the current. So now, if you look at this, R1, dude, it's not doing any division. All the current is going through R1. None of it is being divided by R1. It's all going through R1. I mean, the current actually exists because of the nature of R1. Yeah, so if I were to increase or decrease that, this would increase and decrease. But all of the current, the total current is going through R1. It's being divided amongst these. So these guys are the things that are actually dividing this current. So when we look at how they're dividing it, we need to look at their total and the individual resistance of each one to see how much current each one is actually creating or taking, right? Or dividing, how much it's dividing the current that's going in. So in that case, we'd actually use the exact same formula. Now, so in here, that's going to be 600 because it's going through here. The total resistance here is going to be the total resistance of the two of these. So that's why we don't add this, because that guy is not dividing the current. Hope that makes sense. Okay, voltage divider. Okay, so let's take a look at the voltage divider in this situation, where what we're going to do is we're going to study the voltage here. What I want to do is actually want to find VR4 with the voltage divider. So what I need to do is just kind of unpack this a little bit and see let's unpack the voltages that are in here. So actually just see which voltage is actually being divided. And we're also going to be seeing the total resistance that we use into the voltage divider formula, which I will write here in a second, has nothing to do with this value or that value. Okay, take a look. We know the voltage divider formula looks like this. VR, in this case 4, is going to be equal to VS, okay, bear with me, VS times some kind of ratio of the resistances, and in this case we know the total resistance is on the bottom. Okay, good. So RT, let me write that more better. RT, and in this case I'm going to do R4. Now let's take a look at what this guy means and what that guy means. In our previous example, the IT, when we were doing the current divider, the IT was actually the IT, but in this case the VS is actually different. This is a general form, and we apply this to the part of the circuit that's actually doing the dividing, either current and or voltage. So in this case, my VS is actually, I'm going to label it here. I'm going to put this point here, I'm going to say that's point A. So that's actually my VA. Because essentially, I could actually use the voltage divider to say, hey, you know what? How much voltage is being dropped across this? Or I could say, how much voltage is dropped across this network of parallel resistors, or these two legs. And we know that VA over here is the same as VA over here. That A and that A are the same. We know the voltage potential at this point and that point are the same. Or more specifically, let me write this down. I can say that VR2 equals VR3 plus VR4. Are you okay with that? The reason is because the voltage drop from here to here is the same as the voltage drop from here to here. So therefore the voltage drop of this plus the voltage drop of that is going to have to equal the voltage drop across that. So they're the same. Okay, good. So with that said and done, actually VA in this case is going to be 5 volts. And the reason I kind of put the numbers together like this, let's just kind of do this. I used 600 here, 100 here, and 300 here. So I put those there because before we had a circuit with 600 and 400, and now the total resistance here. So let me just get a different color pen. The total resistance here of this, okay, that RT, okay, let me do that down. Let me just do that here. So in that case, RT, and the total resistance of this. So actually, if I wanted to do the right nomenclature here, I would say RT, I would do this. Okay, let me write this. R, and then I would put 2. I would put 2 in parallel with 3 plus 4. Is that okay? 2 in parallel with 3 plus 4. So the total resistance of these is going to be actually 240 ohms. And the reason is this, because 600 to the negative 1 plus, in this case, 100 plus 300, which is 400. I'll just write that down there. No, maybe I'll do this. 100 plus 400 to the negative 1 to the negative 1 ohms. Okay, so that's the formula for this. I think, you know, if you need to pause and look at that, I don't think you do, I think you get that. And before that, total resistance was 240, because I'm getting that because the last circuit I used for the current divider had the same values. I think that was 600 and that was 400. Okay, so with that said and done, 400, I'm just going to write that down. I mean, 240 equals 240 ohms. Okay. Now let's unpack this guy specifically to say, hey, how do I calculate the voltage across here? Well, we know, I'm not going to do the math for this because it's pretty simple. We know that the total resistance here is 240 and the total resistance there is 240. So that's essentially, it's like doing this, 10 volts. It's no different from this. 240 ohms and 240 ohms. Are we okay with that? And that's 240 and that's in series with another network of resistors whose total resistance is 240. So it's like 240, 240. So we know the voltage drop across that's 5 and we know the voltage drop across that 5. So I can say then pretty simply and pretty securely that VA equals 5 volts. Okay, so I'll leave that there. So now let's actually go here and do this. So I'm going to put these values in here and I'm going to say 5 volts. Now in this case, what am I going to put here? Well, my RT is, first of all, I just put R4. R4 is 300. 300 ohms. What's the RT? The RT is the total resistance of the resistors that are dividing the voltage. The total resistance, in this case, of the resistors that are dividing this voltage is 400 ohms. Because these two resistors are dividing this voltage. So my RT is not the total resistance of the circuit, it's just the resistance of the two resistors dividing the voltage. I was going to say current. Okay, so in this case, it's not 240, it's 400. 400 ohms, and that is 3/4 of 5, which is 3.75. Okay, good. So 3.75. So 3.75 volts. Okay, so the voltage drop across that 3.75 volts, and I think if we can just glean like a full-on lesson of what's going on here, is that when we're using the current divider and the voltage divider, we have to look at the part of the circuit that is doing the dividing, and then take the attributes of that part of the circuit, and then put those into this formula and/or the current divider formula. Cool. So I think we're good, dude. What about